Beautiful. So we're talking about estimating with a certain number of rectangles the area under a derivative curve, right? We did a trig function Monday. Let's do a polynomial today. And the polynomials are the only things we're going to be doing with the Riemann sums. But let's take a look at the integral from 1 to 5 of x squared dx. And so what I'm talking about right from 1 to 5, this particular area. Oops. Right, that area. It's always between the curve and the x-axis. So if the curve is below the x-axis, the area would be below the x-axis, and that area would be negative. And the only thing the negative is telling you, is it above ground, is it below ground, right? Is it up above the axis, or is it below the axis? If you look at my chapter 5 tests, I think I had a negative area on at least one of them. I don't know why I'm coughing. So we're going to get the actual area with a definite integral, right? We get the actual area with the definite integral. What is this antiderivative? What's the antiderivative of x squared? X cubed over 3. And I say evaluate at my bounds, evaluate at 5, evaluate at 1, and that's how I write it. That's how I say it. So I'm going to take x cubed over 3, evaluate it at 5, evaluate it at 1, and subtract them. So what do I get? I get 125 over 3 minus 1 over 3. Agreed? So 125 divided by 3 minus 1 divided by 3. And that's 41.3 repeating, right? Or 41 and 1/3. So we want to do this on the calculator. Every time I ask you to do a definite integral, you're going to do the same thing on the calculator. By the way, anybody notice something weird about this antiderivative, x cubed over 3? You notice anything about it that might seem missing? What's that? Exactly. The constant of integration. And why did I leave that constant of integration out? If I kept it in, 125 over 3 plus c minus 1 over 3 plus c, what's going to happen to the c's, the constants? They're going to go away, right? So we don't bother when we're doing a definite integral, right? We don't bother with that plus c. Did I talk about a definite integral? I did talk about the definite integral, right? I believe 5.2 is the definite integral. Uh, 5.3 are Riemann sums. I don't know if I spelled that right. Let me double check. R-E-I. Oh, no, R-I-E. Oh, I skipped it. I switched it. Riemann sums. And 5.4 is the fundamental theorem of calculus. And that's got two pieces to it. The first piece says the area under the derivative, right? So that's saying the integral from a to b of f prime of x dx is f of b minus f of a, right? That's the first half of the fundamental theorem of calculus. That the integral gives me the area under the derivative curve. And how does it give it to me? I use the original function to find the area. The second piece of it says that, not quite exact, but f prime of x dx is, right, if I'm doing an indefinite integral, meaning no bounds, I don't want the area, I just want the integral to get me back to the original function. I'm starting with the derivative, I'm getting back to the original function, right? And so those in combination will make up the fundamental theorem of calculus. Okay. But kind of what we're doing today is everything. We're doing 5-1, 5-2, 5-3, estimating the area, finding the exact area with a definite integral, and then we're going to show how the estimate can get us to the exact area. That's the Riemann sums. Okay. So back to our problem, we've got the actual area, 41 1/3, whatever units. Who cares? I don't. Right. But now we're going to estimate with 4 rectangles. So we're looking at, again, the area from 1 to 5, right? And we're going to use 4 rectangles, so we're going to cut that base into 4 pieces, right? Yes? And then we're going to go up to the rectangle on the right-hand side, right? On the right-hand side of that first rectangle, that first partition, and that's going to give me my first rectangle. There's my second rectangle. There's my third rectangle. There's my fourth rectangle. And you can see this is going to be an overestimate. I'm going to get something bigger than 41 1/3, right? So we already know that the integral from 1 to 5 of x squared dx is 41 1/3, right? And this particular rectangle, you'll see, these rectangles will give me an overestimate. Is that pretty clear that it's going to be an overestimate? Yeah, so all that little red above the curve is extra, right? And so we want to remind ourselves that we can get this area estimate using the sum from I equals 1 to 4, right? We're using 4 rectangles. So I is the index, first rectangle, second rectangle, third rectangle, fourth rectangle of f of x sub I times delta x. And this is the only formula I use in Calc 1. In Calc 2, I do left rectangles, right rectangles, midpoints, trapezoids, and polynomials, which is Simpson's rule. Okay, so you'll do this again right in Calc 2. As you finish Chapter 5, you'll do all the other estimates of integrals. And so I want to notice, first of all, that delta x in general is b minus a over n over the number of rectangles, right? So for us, delta x for us is going to be 5 minus 1 over 4, which is 1. So meaning every time the base of every rectangle is 1. Do you see that on the picture? The base of each of these rectangles is a width of 1. And so x sub I is, in general, x sub I is a plus delta x times I. So for us, it's starting at 1, right? And we're going to be adding 1i each time. 1i being 1 times 1, 1 plus 1 times 1, 1 plus 1 times 2, 1 plus 1 times 3. Yes, you see what I'm saying? Remember, I is just your counter of the rectangles. So for example, x sub 1 is 1 plus 1 times 1 is 2. Look, that's where my first rectangle ends on the base. X sub 2 is 1 plus 1 times 2. That's 3, and that's my next, right? Do you see it? So pretty clear, the next one is 4, next one and last one is 5, right? So when you're first doing this, it's a good idea to kind of write these things out instead of just think about them. Put it down on paper, right? What is each x sub I? Now, what do I have to do with each x sub I? What does it say I have to do with each x sub I? I have to put it inside of the function. I have to take each right corner of the base of my rectangle and put it inside the function, and that's going to give me the height, right? So this height right here, do you see it as f of 2? The function at 2? And so you can see here, I'm getting, this is the height of the rectangle, and this is the base of the rectangle, right? And height times base is my area, and then and sigma says add them up, right? That Greek letter S, this guy is sigma, right? It means sum, right? So we're adding all of those rectangle areas up to get the estimate of the area under the curve. How are we doing here? We okay? You following me? Yes? You can't just watch me parallel park and be able to parallel park. And I'm good. I always say I'm a city boy. I can parallel park one move. I don't have to back and forth and all of that garbage. One move, right? And so it's the same thing here. You can't expect just to be able to do this. You got to write it out, and you got to be patient, and you will make mistakes, right? So here's my area estimate now. Oh, I'm sorry. I have to find f of x sub I is going to be what? 1 plus I squared. This is probably the hardest part of the whole process, is plugging in that x sub I into the actual polynomial, right? Into the function, and then simplifying it. For me, I'm not going to simplify it here, but you'll see when I do the Riemann sum here, you'll see I will simplify it. So this area is the sum of I equals 1 to 4 of 1 plus I quantity squared times delta x, which is 1, right? Delta x is 1, yes? How are we doing here? This is brand new, right? This is different from anything we've done. So when I put in I for 1 to 4, I get what? I get 1 plus 1 squared plus 1 plus 2 squared, right? Plus 1 plus 3 squared, quantity squared, plus quantity 1 plus 4 squared, right? So that's 2 squared plus 3 squared plus 4 squared plus 5 squared, 4 plus 9 plus 16 plus 25. Help me, 20, 45, 50, 54? Morning. 54, agreed? Did I do that right? Someone check me. 20, 45, and 9 is 50 and 4. Yes. 54, yes? Overestimate, right? We know the answer should have been 41 and a third. This is too much. What happens when I do 6 rectangles? Oh, the area gets closer to 41 and a third. What happens when I do 100 rectangles? It gets closer. What happens when I do an infinite number of rectangles? I get the exact value, 41 and a third. And we're about to do that. Let's double check our actual area on the calculator real quick. And so do this with me, please. So you have your calculators. In y equal, I'm putting in x squared. I like zoom stand. Remember, I have to be able to show on the x-axis my bounds of my integral. And I'm doing the integral from 1 to 5, so I want to make sure I can see 1 to 5. Right? So I'm going to say zoom standard, because I know that shows me negative 10 to 10. There's my function. Everybody with me? Everybody who's going along at home here doing this? And then I do second calculate, and I pick the number 7 as the integral. So pick number 7. And then it's prompting me, what's your lower bound? Where you're starting your integral at? And that's 1, and hit enter. And then what's your upper limit or upper bound? 5, enter. And then it shows me the area, and it calculated, you see it 41.3 repeating. And you see it's not, this little dinosaur brain calculator is not too smart. It can't show me 41 and a third. It's showing me 41.3 and only 6 decimal places, right? But we know we're right now. So when you do one of these definite integral problems on chapter 5 test, you make sure you check it on your calculator, right? so that you know you have that problem correct. Nice. I want to do the problem over with a Riemann sum. So what did I do already? I did this. I got the exact area using a definite integral, right? Find the antiderivative, evaluate. I got an area estimate, right? This is 5.1. So the definite integral is 5.2. The area estimate is 5.1 with a certain number of rectangles. The book gets a little crazy. They ask you to do 10 rectangles, things like that. You certainly could do it in Excel, which would be kind of nice if you could do that. And then for 5.3 is the Riemann sum. We're going to do an infinite number of rectangles. So here we go. So we're talking about a Riemann sum. Riemann is a German mathematician. I don't know what year. I can't remember. So Riemann sum. I need a reminder from pre-cal of some series. Okay. So these are. Sorry, I want to do series from pre-cal. My math majors should go and see the proofs of all of these sums, and they're called proofs by induction. So math majors and computer science majors, proofs by induction for series, okay? My first series, the sum from I equals 1 to n of a constant, which means c plus c plus c plus dot, 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 all the way to that last constant. So we're doing this n times, is n times c, right? If I add up 5 3 times, 5 plus 5 plus 5, it's the same as 3 times 5, right? So that one shouldn't need too much of a proof. That one's pretty easy. The second one is a famous one. The sum from I equals 1 to n of the indices I. So now I'm just summing up the number I. So 1 plus 2 plus 3 plus dot, 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 all the way till I get to what's my very last number. I don't have my ears in, sorry. I thought I heard a mumble, but I can in here. What's the very last number I want to use? What is it? I? Almost. N. Right? I is going up to n. So maybe n is 10. So the last number would be 10. So in this case, I don't know what the last number is, but I do know it's going to be n, whatever n is. And I'm always going to tell you how many rectangles. I will tell you how many rectangles. For me, it's always 4, because it's a lot of work. To do 10 rectangles is a lot of work. Okay? So this turns out to be n times n plus 1 all over 2. And it's a beautiful, beautiful proof out there by Gauss when he was 8 years old. But I want the computer scientists and the math majors to do this proof by induction. So a quick just demonstration of this thing, right? Let's say I equals 1, the sum of I equals 1 to 7 of I, that's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, yes? Help me there. 13, 18, 22, 25, 27, 28, agreed? Will someone check me on that, please? Yep. And then if n is 7, right, I get 7 times 7 plus 1 all over 2, right? I'm using this right-hand side part now, right? So that's 7 times 8 over 2. Oh, that's 7 times 4. Ha ha, same, 28. So when you're playing around with these things, actually get in there and pick values and then write it out and verify it's true, right? Yes, you with me? Don't just look at it. Use pencil and paper and write things out. Because they're very strange at first. They're very, very strange at first. The next one I want you to know is I equal 1 to n of I squared, of the indices squared. So that's 1 squared plus 2 squared plus 3 squared plus dot, dot, dot. And the last one, of course, is n squared. And that turns out to be n times n plus 1 times 2n plus 1 all over 6. Again, math majors, prove that one by induction. You'll probably have to go watch someone else do it at first. But I usually do these in my pre-cal class. Math majors, computer science majors also, please. So I'm doing proofs by induction using a series. Series means the sum. Those are the sums. Khan Academy is probably a good choice. I think he's brilliant. He's just boring. Puts me asleep when I watch it. I can't open it. Oh, here. So here's that first one, right? This is the one that Gauss proved pretty damn quickly. So you probably couldn't even put that series in, right? If I just Google n times n plus 1 times 2n plus 1 all divided by 6, I probably will see yeah, so you can just type that series in directly and you should find the proof of it. So math majors, computer science majors, you want to be able to do those proofs. Math majors are going to do you should do Math 207, Computer Science 207, which is called discrete structures. It's discrete math where you prove everything. And then when you transfer to university, you'll take a bridge to abstract mathematics where you'll prove even more things. And then in every class you take after that, you prove everything you do. So, and then computer science majors want to understand the structure of proofs because that's what the computer understands. So, so you'll take that here as a part of your associate's degree, right? And our Math 207, Computer Science 207, is identical to College Park, okay? So, one more. The series from I equals 1 to n of the indices cubed is 1 cubed plus 2 cubed plus 3 cubed plus dot, dot, dot plus n cubed is n squared times n plus 1 quantity squared all over 4. So those are the 4 that I would like you to have, right? This was just an example. I'd like you to have all 4 of those on your formula sheet. If you do enough of these problems to practice, you'll have them memorized. And I'm always saying that as we get to the final exam. Are you going to have everything from all 4 chapters on your formula sheet? Probably not. You're going to have to eventually say, oh, I know the trig now. I don't need the unit circle anymore. Take it off, right? Of course, if you're nervous about things and you get lock brain or whatever you would call it on a test, you want to have as much on as you can, right? So I'm going to use these in a second. I want to go back to my Riemann sum for a second and take a look. I already know the integral from 1 to 5 of x squared dx is 41 1/3. Oops, x squared dx. I want to show that also equals the limit as n goes to infinity of the sum of the rectangles from the first to the last of f of x sub I delta x. So I'm going to do an infinite number of rectangles. That limit's going to tell me the number of rectangles goes to infinity. But I have to figure out what my delta x is. Remember, it's 5 minus 1. It's b minus a over n. So that's 4 over n. My x sub I is 1 plus delta x times I. And here comes the tough part. F of x sub I is x sub I squared, right? So that is 1 plus 4i over n quantity squared. And this is probably the toughest part about this. But is everybody with me here? Everybody following me? Lillian, no? Yes, you're okay? Yep. Everybody okay? We just did this a second ago with 4 rectangles, right? So, and we knew n was 4, but now we don't know what n is. So in every formula, I got to keep n as a variable because it's going to be 1,000 rectangles. I'm sorry, no, 10 million rectangles. No, 7 billion, 200, right? It's going to, the rectangles are going to get more and more and more. And what happens, imagine what happens when I have so many rectangles, what's happening to the base? It's getting smaller and smaller and smaller. So imagine the base is as small as the width of my pen tip, right? Do you see how close it is to getting the exact area? And so when I take this limit, what does this piece become? When I take the limit, what does that piece become? What letter is that? Greek letter what? S, sigma, right? So S, do you see an S on the left-hand side? The integral is an S, do you see it? It means sum. What happens to delta x? What does that become? Guess. Say it. Not x sub I. Look at the parallel pieces, right? Look at the side-by-side pieces. What does dx seem to relate to in terms of location? Dx. Delta x is x2 minus x1, right? 5 minus 1, right? But what's dx? Infinitely small base of the rectangle. So small, it seems like it's 0. But it's not. It's infinitely small, right? Inside of dx is also my 5 to 1, right? And the only thing that's kind of really left is the f of x sub I. That's just my original function, whatever function I had. That doesn't change. So I want to expand this out. Let's see, I get 1 plus 4i over n times itself. I'm only going to do this once, so in the future I'll just expand it out quickly. This is 1 plus a 4i over n plus another 4i over n plus a 16i squared over n squared. And so you see I get what? 1 plus 8i over n plus 16i squared over n squared. And that is what I'm going to use as the height of each rectangle. Right? Here's the base of each rectangle. Here's the height of each rectangle. So we're trying to show that 41.1 is equal to the limit as n goes to infinity of the sum of I equals 1 to n of that height, 1 plus 8i over n, plus 16i squared over n squared, times the base, 4 over n. Make sure you're with me. Don't let me go on if there's some confusion. If you came in late, I am recording. Hey, everybody's here. Is that true? Do I have 20 students left only? No, I should have 22. Who's not here? Oh, Asir's not here. Asir, are you back there? No? Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, yes. How are we doing? We're okay? Good. Around this time, I get bored a little bit, so I start writing my limit as just an L, and I start writing my sum as just a sigma, right? And then I'm going to distribute in here, right? This is 4 over n plus 32i over n squared plus, 4 times 16, is that 64? 64i squared over n cubed. And if I'm doing the sum of a plus b plus c, it's the sum of a plus the sum of b plus the sum of c, right? We should all be able to agree with that. So I want to split up this sum into as many sums as I need. And what's going to happen on your chapter 5 test is you're going to get the area right on the calculator. You're going to get the area right with the definite integral. You're going to get the area wrong with this sum. And it's a pain in the butt, especially if you don't practice. But you can't get nervous, and you won't be able to see your mistake. So you do the rest of the test and then come back to this sum at the end. Okay? I've seen it many, many, many times. You just make one little simple calculation error and it throws the whole thing off. What is the sum dependent upon? What variable is the sum dependent upon? What variable is the sum dependent upon? N? Almost. I. Because n is going to be told to you. It might be 4. It might be a billion, right? So n is eventually fixed. What makes n go all the way to infinity is the limit, right? So the limit is dependent upon n. The sum is dependent upon I. Okay, so that means anything I have here, that's not an I can move outside of this sum. So I'm talking about the limit of 4 over n times the sum of 1 plus 32 over n squared times the sum of I plus 64 over n cubed times the sum of I squared. The only thing the sum depends on is the variable I, right? Or the sum of a constant, the sum of the indices, the sum of the indices squared, right? And we have a formula for each of these, right? I wrote those out on that previous page here. I got a formula for each of these series, right? That is in your book, by the way. It's in 5.3, that whole list, okay? But I'm going to use them now. Oh my gosh, my computer's starting to slow up. Don't do it to me. I hate technology. I don't hate technology, but it's just crappy sometimes. So what's the sum of 1? 1 plus 1 plus 1 plus 1, n times. N, right? And the sum of I is n times n plus 1 all over 2. And the sum of I squared is n times n plus 1 times 2n plus 1 all over 6. So I can simplify some things here, right? The n's cancel in this first piece, so I'm going to get a sum of 4 for that first thing. N and n squared cancel, 32 and 2 cancel, so I get plus 16 over n times an n plus 1. On the next one, the n and the n cubed cancel to an n squared. And 64 over 6 is, don't tell me. Oh, it's low battery. 10 and 10 2/3. And then I get n plus 1 times 2n plus 1. And so what I'm doing is I'm just trying to, why is it not changing to black? Change to black, change to black, magically, there it is. I'm just trying to simplify as much as I can. And we're going to go back to chapter 2 in a minute. Now, I want to distribute, okay? Before I do anything else, I want to distribute. So I know I'm going to have a 4. I'm going to have a 16n over n. I'm going to have a 16 over n. 10 2/3, I don't like the way that looks. Let me do what? 32 over 3? Over n squared, and I get 2n squared plus 3n plus 1, right? I just foiled that piece, yes? And I'm still distributing here, but as I go, I can simplify a little bit more. And don't let me go too fast. I feel like my coffee's kicking in. If I'm going too fast, you can slow me down. So I get a 4 plus a 16, right? Do you agree? Those n's cancel. Plus a 16 over n. I get 64 over 3 times n squared over n squared plus 32n over n squared plus 32 thirds over n squared. I'm distributing, right? And please, if you're doing this with me or you're watching, check me. Make sure I don't make a mistake. If I make a mistake, just tell me. And don't say to me, Robert, you became a math teacher and you're living in D.C. That's your mistake, because I already know about all those mistakes. It looks like I can cancel a few more things here, right? I've got 20 plus 16 over n plus 64 over 3 plus 32 over n plus 32 thirds over n squared. And just about ready to take my limit. So I try and simplify as much as I can down to this. There are other options, but this is what you're going to do the first time you try one of these problems. There are other ways to get there quicker, okay? But this is what I want you to do when you first do one of these Riemann sums. So what's the sum of anything divided by a very large number? What's the limit of anything divided by a billion? Any number divided by a very large number is going to go to where? 0, right? So I'm going to get 20 plus 0 plus 64 over 3 plus 0 plus 0. So I get 20 plus 60 over 3 should be my answer. What is that? That's 60 over 3 plus 64 over 3. 124 over 3. Yeah? You remember when we did our actual definite integral? Let's look at that definite integral before I simplify this. Come on, computer. Damn it. 124 over 3? Yeah. I'm just going back to where we did our definite integral today. Look at it. 124 over 3. No, 125 over 3 minus 1 over 3. 124 over 3. 41 and a third. Exact. When I go to an infinite number of rectangles, I get the exact area. I get exactly what the definite integral gives me. Yes, question? Yeah, so the limit of 16 over n as n goes to infinity. So 16 over a billion, 16 over a godzillion goes to 0. Anytime the denominator dominates, right, my limit's going to go to 0. Yeah. So all of these in the red circles here all go to 0. Pretty cool, right? It takes patience. It takes practice. You got to be neat. You have to kill a tree. I don't care about trees. Kill a tree, pass the class. And then when you become a biologist or a computer scientist or a famous mathematician and you're making over $100,000 a year, go plant a couple trees for Calc 1, plant twice as many for Calc 2, right? And you'll make up for all the paper you're using. And if you need paper, I'll give you paper. Okay? Nice. Let's take a look at our chat. Let me stop this recording, first of all. I'm trying to get my